In a previous video, we talked about the Euclidean algorithm, which is an algorithm that you can use to find the greatest common divisor of two integers. So let's review how that works. So, review of the Euclidean algorithm. Once we review this, we're going to extend this and figure out how to write the GCD of two integers in terms of the two integers you started out with. And I'll explain that when we get there. But for now, let's just review how to find the greatest common divisor of 2024 and 748. So this is the same example as in a previous video. And one way to do this is to factor 2024 and 748, but in the Euclidean algorithm, you don't need factorization. First, we see how many times 748 goes into 2024 and then calculate the remainder. So the first equation we get is 2024 is 748 times 2 plus 528. Okay, so this tells us that the GCD of 2024 and 748 is the same as the GCD of 748 and 528. And we repeat the same process, so 748 is 528 times 1 plus 220. And so it's the GCD of 528 and 220. So then we repeat the process. 528 is 2 times 220, or 220 times 2 plus 88. So now we need to find the GCD of 220 and 88. And we do it again. 220 is 88 times 2 plus 44. Now we need to find the GCD of 88 and 44, which we can see since 88 is 44 times 2 plus 0, we see that the GCD of 88 and 44 is 44. So the GCD of 2048 and 748 is 44. So it's a fast algorithm for finding the greatest common divisor. And now we're going to get to the title of this video, the extended Euclidean algorithm. So what the extended Euclidean algorithm is a way to write the GCD in terms of the two numbers you started out with. So we can write this GCD as 2048m plus 748n for some integers m and n. Well, we know that the GCD in this case is 44. So we can find integers m and n such that 2048m plus 748n equals 44. Okay, how do we do that? Well, we use the equations that we found before. So if you look at the first equation, okay, so we have these two starting numbers, 2048 and 748, here and here. And we can write 528 in terms of those two numbers. Now 528, if you look at equation 2, is 748. Well, 748 is 528 times 1 plus 220. So if I can write 528 in terms of 2024 and 748, then I can use the second equation to write 220 in terms of 2024 and 748. And then I can just keep going until I get to 44. So that's the idea. Okay, let's actually write down how it works. So you look at the first equation and get 528 by itself. So that's 2024 minus 748 times 2 equals 528. So that's from the first equation. So the first equation implies that. Okay. Now, I know that the second equation, so the second equation says that 748 is 528 plus 220. Well, now I'm going to replace the 528 with the equation that I just found. So equation 2 tells me that 748 is 2024 minus 748 times 2 plus 220. Okay, so when I solve for 220, I get 748 minus 2024 plus 2 times 748 equals 220. So what that tells me is that negative 2024 plus 3 times 748 is equal to 220. So now I've expressed 220 in terms of 2024 and 748. Now I'm ready to go into the third equation, and now I want to get 88 in terms of 2024 and 748. So equation 3 tells me if I just replace 220 by what I have before, it's 2024 minus 748 times 2. So let's see. What am I doing? Okay, so this 2024 minus 748 times 2, that's equal to 528. That's from here. Okay. So that's 528, and then it says equals 220, so it's equal to, now I use this equation. Right? So it's negative 2024 plus 3 times 748 equals plus 88. So now I can solve for 88. So I'm just going to move this over to the other side. So you get oh, I didn't multiply this by 2. Let's see. Oh, right. There's a 220 times 2 plus 88 in equation 3. Okay, so I move this whole thing over to the other side, and that's going to give me 3 times 2024 minus 8 times 748 equals 88. Okay, now I keep going. I use equation 4, so that tells me that 220 minus 88 times 2 is 44, right? And so now I just replace 220 and 88. So I get negative 2024 plus 748 times 3 minus, and then my 88 is 3 times 2024 minus 8 times 748. So that times 2 equals 44. And finally, when I simplify, I get negative 7 times 2024 plus 19 times 748 equals 44. And if you calculate it out, it turns out to be correct. So in general, given two integers a and b, there are integers m and n such that the GCD of a and b is equal to am plus bn. And the algorithm that we demonstrated, so we start off with the Euclidean algorithm, right? And then you just use the equations that you found and just substitute in until you get to expressing the GCD of A and B in terms of A and B. More precisely, is A times an integer plus B times another integer. So this algorithm that we showed of not just finding the GCD, but explaining how the GCD is expressed in terms of A and B is called the extended Euclidean algorithm. So this is a useful thing if the greatest common divisor of A and B is 1. So in particular, so the Euclidean algorithm, the extended Euclidean algorithm works even if the GCD of A and B is not 1, but it's often more useful when the GCD is 1. So if the GCD of A and B is 1, then there are integers m and n such that A times m plus B times n is 1. And one way this is useful is if either A or B is prime. So an application of this fact is, suppose that B is a prime, okay, let's call it P, and that the GCD of A and B is 1. So in other words, P does not divide A, right? So A is not a multiple of P. Then by the extended Euclidean algorithm, we can find integers m and n such that am plus pn is 1. Okay, now what happens if you reduce mod p? Then, okay, then you get, well, the pn is going to reduce to 0, so you're going to get a times m is congruent to 1 mod p. So what does that mean? That means that you found an integer m such that a times m is congruent to 1 mod p. So that's the multiplicative inverse. M is the multiplicative inverse of a mod p. So in another video, I'll do an example of using this to calculate the multiplicative inverse. And then we'll also use this extended Euclidean algorithm to prove an interesting property about prime numbers.